Hi folks, this is Nat, and this is going to be a video lesson on calculating compound probabilities for independent events. Independent events are events that don't affect one another, so the outcome of the first doesn't change the outcome of the second. The other goal is that we want to be able to multiply fractions because that's an essential skill for being able to calculate compound probabilities. Let's start by talking about what a compound probability is. It's basically the probability of one event and then another. Another way to say it is that it's the probability of multiple outcomes occurring together or one after another. For example, if I was going to flip a coin more than one time, compound probability would be how I figured out the probability of getting heads then heads again. And anytime you are calculating compound probability, you will typically expect to see it with the words and or then. For example, if I said, what's the probability of flipping heads then flipping tails, that's compound probability. If I said, what's the probability of rolling a 4 on a 6-sided dice and also rolling a 2 on a 4-sided dice, again, that's compound probability. I can recognize it pretty easily by looking for those keywords, and then. The other thing to know is that compound probability is really heavily based around the idea of combinations. We talked before about how different things can be combined together into lots of different combinations. And we can find out how many combinations are possible by multiplying the different possibilities together. You'll find that when you're doing compound probabilities, you're doing the same thing. As a quick reminder, let's say I have 3 shirts, 2 pants, and 4 hats, and I want to know how many unique combinations of shirts, pants, and hats I can put together. Well, to do that, I'm going to do 3 times 2 times 4, 3 pants, or 3 shirts times 2 pants is 6 options, and then times 4 additional hats is going to be 24 total combinations. That's going to be, again, really pivotal in any idea of compound probability, because if I'm asking questions like what's the probability of getting one of those particular shirts in any combination, I'm going to be multiplying that together as well. I'm going to need to know the total combination, so I'll be multiplying things together a lot. Which gets us to the big idea of the relationship that is in compound probability. If I'm talking about the probability of event A and event B happening together, it's just equal to the probability of A times the probability of B, which ends up being a pretty simple equation to work with. If I want to find compound probability, the event A then event B, or A happens and B happens at the same time, all I have to do is say what's the probability of event A, what's the probability of event B, and I multiply them together. Here's an example. Say I'm rolling a regular 6-sided die, and I'm interested in basically the probability of getting 2 6s in a row, the probability of rolling 2 6s. The first thing to do is actually separate this idea out into the 2 individual events. So it's sometimes helpful to rewrite this idea of the probability of rolling 2 6s. To me, that means the probability of rolling a 6 and then, there's that word, or both words really, and then, rolling a 6 again. So I'm really talking about the probability of rolling a 6, then rolling a 6. Now, each of these, rolling a 6 and rolling a 6, is an independent event, not affected by the other. So in this case, since they're the same event, they're going to have the same probability. And hopefully at this point, you know that the probability of rolling a 6 is 1/6. 1/6. One of the 6 sides of a die is a 6. And so rolling a 6 again would also be 1/6. And the probability of doing both is going to be those 2 fractions multiplied together. You might think of the then as being basically like a multiplication keyword in probability. So I'm going to be doing 1/6 times 1/6. Thankfully for us, multiplying fractions is really simple. You just multiply straight across the top, straight across the bottom, you have your answer. And in this case, 1 times 1 is 1, and 6 times 6 is 36. And that's my compound probability, the probability of rolling 2 6s. I have a 1 in 36 chance of rolling 2 6s, meaning that 1 out of the 36 times that I roll a dice twice, I would expect to get 2 6s. Here's another example. Let's say this is a spinner and it looks like it has 3 pink spaces, 2 red spaces, 2 purple spaces, and 1 orange space. Let's say I wanted the probability of rolling first pink, then purple. Well, again, I've got that keyword in here that tells me, first of all, then, that I'm going to be multiplying. And at this point, it's just the 2 individual probabilities. Spinning pink, then purple is the probability of spinning pink times the probability of spinning purple. So, spinning pink, it looks like there's 3 out of 8 spaces are pink, and I'm going to be multiplying that by the probability of spinning purple, which is 2 out of 8, or 1/4. Always nice to simplify fractions, because I'll have to do it at the end if I don't do it now. So, again, I get to multiply straight across. 3 times 1 is 3, and 8 times 4 is 32, meaning that the probability of spinning first pink, then purple, is going to be 3 30-seconds. So calculating compound probabilities ends up being pretty simple, at least provided we are very specific about what we're looking for. The less specific you are and the more ways you can get it, the more complicated this can get. Let's change my probability just a little bit here and say, what's the probability of just spinning pink and purple when I do it twice? This is trickier because now we're talking not about one specific thing, first pink, then purple, but a couple different possibilities. If I just want 1 pink and 1 purple, well, I could spin 1 pink and then 1 purple, or I could spin 1 purple, then 1 pink. So it might be worth rewriting this and thinking about it like this. So here we go. The probability of 1 pink and 1 purple is really the probability of pink then purple, or purple then pink. So now I've got a whole bunch of compound things that I need to be thinking about. A couple keywords to look at. We've got then. Okay, and over here a T that I had to squeeze in for then again. And then we've also got or, which if we remember is not a multiplication word. I'm going to do this the same way though. So we're going to do pink then purple, the probability of pink then purple. That's 3/8 times 1/4 like it was before. And then we've also got purple then pink, which is just going to be the opposite order, same stuff. The probability of purple is 1/4 times the probability of pink, which is 3/8. So individually, each of these is going to be 3 30-seconds and 3 30-seconds. The last thing to really think about is this or word here. When I look at this or, if you remember, or means addition. So the probability of this or the probability of this means the probability of the first one plus the second. So I'm going to throw in some addition to finish this up. So 3 30-seconds plus 3 30-seconds, thankfully they have the same denominator, is going to be 6 30-seconds. So my total probability of 1 pink and 1 purple is 6 30-seconds, which I might reduce down to 3/16. 3/16 of the time I'll spin 1 purple and 1 pink when spinning this spinner twice. So as you can see, one of the things to know about probability, and hopefully you've gotten this impression before, is that the combinations of things can stack up pretty fast, and things that might start looking simple actually might be more complicated than they initially seem. Finally, you really can't talk about compound probabilities without talking about multiplying fractions. And there's not a whole lot to say in terms of what to do. It's a pretty simple thing, thankfully. It's not nearly as difficult as adding or subtracting fractions. But any fractions you might want to multiply together, let's say 3/5 times 2/4, you don't need a common denominator, which is nice. What we do is we simply multiply straight across the fraction. Numerator times numerator, denominator times denominator. So in this case, 3 times 2 makes 6 in the numerator, and 5 times 4 makes 20 in the denominator. There's lots of ways to simplify fractions. In this case, I'm just going to reduce that to 3/10. There are also ways to simplify as you're multiplying called cross reduction, but we won't get into that here. For the sake of compound probability, all you have to know is that when multiplying fractions, multiply straight across, numerator times numerator, denominator times denominator. The other thing that's worth noting about multiplying fractions is, because it sometimes confuses students, especially when they multiply a whole number by a fraction, is that when multiplying by a fraction, you always end up with a number that is less than the number you started with, or the fraction you started with. As you can see in this example, 3/10 is less than either of the two fractions that it came from that were multiplied together. When we multiply by a fraction, we're actually reducing. It's the same thing as dividing, actually. Multiplying by a number less than 1, a fraction, is like dividing. And the interesting thing about that relating to compound probability, then, is that because that's always the case, compound probabilities are always less likely to occur than their individual piece probabilities. So if one event has a probability of 3/5, the other has a probability of 2/4 or 1/2. When I say one event and then the other, and I multiply them together, I end up with a probability of both happening together that's less than either of the original two. So it becomes less and less likely to happen the more events we compound. And here are your practice problems. All three of them refer to the spinner here on the left, which, if you can't count, has 10 spaces. Good luck. Enjoy.